Aha! Good day, students. I welcome you to your favorite YouTube channel, Physics for Everybody. Today, we'll be solving the May June 2024 Cambridge IGCSE Physics 0625, Paper 4 Variant 1. Without delay, let's start. But let me just chip this in, okay? In order to make these things easier for you to understand, we'll be using a PhET simulation to explain concepts. We'll also be using, we're using PhET simulation to explain concepts about nuclear radioactivity and electric circuits, okay? And at the end of this discourse, I will briefly take you through concepts like the life cycle of a star and how Newton star can the concept of Newton star, how Newton star combine to form a black hole, and that was it. So those are the other things that will be chipping in. So please stay tuned. We start with question number one. A tube contains oil. A small ball is held up vertically at the surface. Okay. All right. The first thing you have to do here is to define acceleration. What is acceleration? So this is the definition of acceleration, the change in velocity per unit time or change in velocity with respect to time. We take the next question. The mass of the ball is 0.075 kilogram. Calculate the resultant force on the ball when it is accelerating downwards at 2.8 meters per second square. And you know the formula for force equals to mass times acceleration. The mass is 0.075. The acceleration is 2.8. By the time you multiply those two, this is what you have. You get 0.021 Newton. Yeah, in order to conserve time, I've done this paper before. All right, we go to the next question. Okay, let me come here. The next question says, as the ball falls, its speed v is recorded. Figure 1.2 is the speed time graph for the falling ball. Describe what happens to the acceleration between t equals to 0 and t equals to 0.04. Okay, 0.0 and 0.04. What happens to the acceleration now? So as you can see here, since the vertical axis gives us the velocity, that simply tells you that fine, velocity is increasing, but after some time, velocity stops increasing completely. At that point when velocity is increasing, we have acceleration. But what kind of acceleration is this? This is decreasing acceleration. Okay, yeah. So what happens to the acceleration of the ball? The acceleration of the ball is decreasing. Okay, it's decreased until it became 0. Okay, yeah. At constant velocity, acceleration equals to 0. Yes. So that's what happened to the acceleration of the ball. Okay, and what caused that is the water resistance. Sorry, the resistance oil. This is oil, not water. Yes. So it's the resistance force due to the oil. That's what caused the acceleration to decrease. Okay. Yeah. And acceleration continues to decrease until this resisting force becomes equal to the resultant force. That is the weight of the ball. When these forces are equal, then acceleration becomes 0. These are written grammatically here that the acceleration decreases gradually until it becomes 0 and continues to remain at 0 for the rest of the motion. So this decrease in acceleration is because the resistive force, which is oil resistance, okay, is not water, it is oil in this case. It increases as the speed increases, okay, hence the resultant force on the ball decreases until it becomes 0. The ball therefore travels at constant speed, called terminal velocity. So this constant speed here is called terminal velocity. Okay, so we take the next question. By drawing a tangent on figure 1.2, determine the value of the acceleration of the ball at t equals to 0.01 second. Now, this is what you do. You come to 0.01 second, trace it to the curve, and you produce a tangent here. That I have done. When you draw this tangent, since this line here, since this line here is tangent to the slope at 0.01 second, therefore the gradient of this line here gives you the acceleration at 0.01 second. So that's what we are doing. So when I drew this line, I got my values, okay, I want to draw it as if you are drawing a big right angle triangle to calculate the value of to calculate the slope. So the value I have up here is 0.05 meters per second. The value I have down here is 0.4. Then I'll trace it down here. The value of time here is 0.2. The value of time down here is 0. So I'm trying to calculate the slope of this right angle triangle. Yes, so that same concept, that's what I'm doing here. So I pick my values, I put them here. So this is the value of final velocity 0.05 minus 0.04 divided by 0.02 minus the starting time here is 0. I got 0.26 divided by 0.02, which is 1.3 meters per second. And that is what I put here. Okay. Yeah, that's it. So as long as my value is correct and my calculation is correct, I will get the total mark for that question. We go straight to the next one. So the next question, question number 2. Figure 2.1 shows two identical trolleys P and Q held at rest on a frictionless horizontal surface. A load is fixed to trolley P. This is the load is attached to trolley P. There is a compressed spring between trolleys P and trolley Q. This is the compressed spring. The trolleys are released. As the spring expands, it pushes the trolleys apart. Trolley Q moves to the right at constant speed of 0.36 meters per second. Trolley Q moves to the right. Velocity of trolley Q, that is a constant speed of 0.36 meters per second. The mass of each trolley is 1.2 kilogram. 1.2 kilogram, the mass of each trolley. The mass of the load on trolley P is 1.5 kilogram. That is already stated here. The spring has negligible mass. Calculate the speed at which trolley P moves to the right. Remember the concept of the formula for conservation of linear momentum. Total momentum before collision was equal to total momentum after collision. And from that formula, we have m1u1 plus m2u2 equals to m1v1 plus m2v2. So that's the formula we are using to solve this question. Okay. So after writing out the formula, you write out the mass of this. I'm taking this as my object number 1. So mass of this object, total mass of this object will now be 1.2 plus 1.5. So m1 will be 1.2 plus 1.5, which is 2.7, multiplied by what is the initial velocity of this object. Initial velocity of this object was 0 because it was at rest, plus m2 is the mass of trolley Q, which is 1.2. Initial velocity of this object Q was 0 because initially it was at rest. Now, when the spring pushes them apart, which is where we have the final velocity now, m1, which is 1.5 plus 1.2, which is still 2.7, 2.7 times my m1 is 2.7. What's v1? Final velocity of this object, that's what we are looking for, okay? We're looking for the final velocity of trolley P, okay, which is, so we do not know it. Plus m2, what's the mass of trolley Q? 1.2. Final velocity of trolley Q. We have final velocity of trolley Q as 0.36 meters per second. Now let's go. 2.7 multiplied by 0 gives you 0. 1.2 multiplied by 0 gives 0. 2.7 times V1, 2.7 V1 plus 1.2 multiplied by 0.36, that will give you 0.432. So let's see, this is 0. Take this one to the other side, so I have minus 2.7 V1 equals to 0.432. To make V1 stand alone, I'll divide both sides by minus 2.7. So I'll have V1 on the left hand side equals to 0.432 divided by minus 2.7. Press that on your calculator, you get minus 0.16. Okay. Take note that this negative sign simply means that the fact that I'm taking this velocity to the as velocity to the right, then it simply means the negative velocity simply means the velocity is to the left. Okay, and that's what I'm indicating with this arrow. The fact that I have a negative sign simply means my velocity is to the left, and the value of that velocity is 0.16 meters per second. That's the final velocity of trolley P plus the load on it after the spring expands. So that is it, and the velocity is to the left. Now the question is asking us for the velocity of with which trolley P moves to the left. The statement has already told us that it is to the left. So what we just need is just the numerical value, the figure. We don't need to put the minus sign because the minus sign is telling us to the left, and the question is already telling us to the left. So if I put the minus sign here, it's the tautology. Like, yeah, so there's no point. The second thing here is kinetic energy of trolley Q when it moves at 0.36 meters per second. Where is trolley Q? This is trolley Q. We have the mass, right? What's the formula for kinetic energy? Kinetic energy equals to half mv squared, which is half multiplied by the mass is 1.2. The final velocity is 0.36, so we just have 0.36 square. Press this on your calculator, you will get 0.07776. So we express that to two significant figure. Why two significant figure? Because all the values in the question are expressed to two significant figure. Express this to two significant figure, you have 0.078 joules. That's all. The next question, state the energy transfer that takes place as the spring expands. What energy transfer? Initially, the spring was compressed, so it had elastic energy, or you call it elastic potential energy. And when that string expands, this elastic energy will be changed to kinetic energy, and it is that kinetic energy that pushes the trolleys apart. So we have elastic energy is converted to kinetic energy. That is all for question number 2. Let's move to question number 3. Figure 1.3 shows a small block of ice floating in a beaker of warm water. State one way in which motion of particles in ice differs from motion of particles in water. Particles in ice. Ice is a solid, right? Yes. Particle in water. Water is a liquid, right? Yes. So particles in a solid are held in fixed position. Okay, they cannot move about. They can only vibrate about that fixed position. Particles in water. Water is a liquid. Particles in water are free to move about, though they are also vibrating. Okay, particles of water also perform that vibrational motion, but while vibrating, they can move about, they can change position. But particles in a solid can only vibrate about one position. They are not free to move about. That's the distinction between particles of a solid and particles of a liquid. Let's move to question number 2b. Oh, I've already written it there. It's fine. Energy is transferred from water to block of ice. State the name of the thermal process that transfers energy from water to ice. It's conduction. Why? Because water is being transferred from, heat energy is transferred from water to ice due to surface contacts between water and ice. But the question asks you the process by which energy is being transferred within the water. Within the water alone is convection current within the water. But between water and ice is conduction because it's due to the surface contact between both of them. We go to the next question. Okay, we are performing a calculation here. Let me do that here. So the next question asks us that initially there is 0.34 kilogram of water in the beaker. Mass of water is 0.34 kilogram. The specific capacity of water is 4200 joules per kilogram degree Celsius. Okay, let's go. Calculate the energy transferred from this water as its temperature decreases from 28. Change in temperature is 28 degrees Celsius to 10 degrees Celsius. So temperature is reducing. So our change in temperature will be initial temperature minus final temperature since temperature is decreasing. And if you choose to use final temperature minus initial temperature, is fine, but your answer will be negative sign. The negative sign simply means that heat energy is leaving the water molecules. Yeah, so let's do it that way. Quantity of heat is mc theta 2 minus theta 1. Don't forget that theta 2 means final temperature. In this case, our final temperature is 10 degrees Celsius and the initial temperature here is 28 degrees Celsius. It's fine, let's use it. Um, Quantity of heat energy is the mass, which is 0.34 times specific capacity is 4200 times change in temperature will be theta 2, which is 10, minus theta 1, which is 28. So I will have 0.34 multiplied by 4200 multiplied by minus 18. If you multiply all of these together in order to conserve time, if you multiply all of this together, you get minus 25,704. This is what you get, okay? And we express it to two significant figure, which is two significant figure, that will be minus 26,000 joules, right? Yeah, and why do we neglect the negative sign? Because the question tells us to calculate energy transferred from water. We have to calculate the energy that is leaving water. If energy is leaving an object, then change in energy will be negative. So since they have already told us that the energy is leaving the object, then there's no point emphasizing on that negative sign again. Just put the magnitude there. But if you're asked to calculate the change in energy, then you have to put the negative sign, letting us know that energy is leaving the water and going into the ice. Yeah, yes, thermal energy flows from the hot object to the colder object. So energy leaves water and go to ice. So that's how I got 26,000 joules. Is it 26,000 joules? Yes, 26,000 joules. Or you write 26 kilojoules, your choice. Temperature of water near the ice decreases first. Explain how convection causes the temperature of all the water in the beaker to decrease. Aha! Now you are explaining convection. How convection causes the temperature of water in all the beaker to decrease. What happens? Since ice is cold, water molecules that are close to ice will lose their thermal energy. They will become dense, heavier than other molecules of water. Hence, they will fall to the bottom of the beaker. As they are falling, what happens? As the as the cold water falls to the bottom, warm water that's in beaker would rise to the top to take up the space. Okay? Otherwise, there will be void here. There will be void. And according to physics, we cannot have void here. So warm water at the bottom of the beaker would rise to the top. When they rise to the top, what happens? They they move closer to the cold water and the ice. They also lose their heat energy. When they lose their thermal energy, what happens? They become cold. The moment they become cold, they become denser, and then they will also fall to the bottom of the beaker. Okay? They get to the bottom of the beaker, warm water from the bottom of the beaker again would rise to the top. And that is what creates the convection current. So that's it. And you want to write this down? This is how you put it in writing. Without delay, let's move to the next question. Okay, so I think this is the one we just did. Okay. Describe the change. Okay. Oh, no, no. The last question. State what happens to the internal energy of water as the temperature of water decreases. Describe the change in terms of energy of particles. So as the temperature of water is decreasing, what happens to its internal energy? But we want you to go into details and tell us in terms of energy of particles. What is happening to the energy of the particles? The energy of water molecules, kinetic energy of water molecule decreases as the temperature decreases. Hence, since the kinetic energy is decreasing, then it simply means the particles will be the they possess less internal energy. Yeah, that's what happens. Okay, so the kinetic energy of the particles decreases. Okay, so they'll possess less internal energy. So that is it, and that's how I've written here. As temperature of water decreases, the kinetic energy of the molecule decreases. So this causes its internal energy to decrease. Now we move to the next question, question number 4. Let's see what we have here. The lens in a magnifying glass is a converging lens. Figure 4.1 shows the lens of the magnifying glass. Its two focal points, f1 and f2, and its principal axis. State what is meant by focal point. Focal point is just the point, okay? It's just a point along the principal axis where rays of light that are parallel to the principal axis. So if I have rays of light that are parallel to the principal axis and they are close to the principal axis, if these rays of light are considered parallel to the principal axis, they are close to the principal axis and they are moving towards the lens. After refraction through the lens, what happens? They are all going to converge at the principal focus. Yes, that's what we mean by convergent lens. Rays of light that are parallel to the principal axis and close to the principal axis, they will all converge at the focal point. Okay? Does it mean that they'll stop moving at the focal point? Of course not. They'll continue to go on their own straight path. Light travels on a straight line. But if I have an object here, if I have a screen here rather, then the image will be formed on the screen. Yes, I believe that is clearly understood. So how would you put this in writing? These I've put in writing here. So the principal focus is that point on the principal axis where rays of light that are parallel to the principal axis and incident on the lens would converge after passing through the lens. Okay, we continue to the next part of the question. A student using the magnifying glass sees a magnified image of an object. On figure 4.1, mark a point on principal axis for a possible position of the object. So you mark this point, you mark X where the object is likely to be placed. Since you are using the converging lens as a magnifying glass, then the object must be placed between the principal focus and the lens. The object must be very, very close to the lens, okay? Hence, it must be placed between the principal focus and the lens. Let me open a PhET simulation to explain this. So looking at what we have here, this is an object and this is the image, the inverted image, real image formed, okay? This horizontal line here that passes straight through the center of the lens is called principal axis. Now, if the object is far from the lens, we have real image, okay, being formed. But if you want to use it as a magnifying glass, that means you want the image to be big, enlarged. To make the image enlarged, then take note. Look, take note that as you are bringing the object closer to the lens, image gets bigger. Yeah. So when the object gets to the principal focus, what happens? Image will be formed at infinity. Okay, but if you bring the object closer than that, take note that the image very close to the principal focus though, the image will be enlarged though, okay, but still an inverted image and is a real image, okay. But what the magnifying glass forms is a virtual image, okay. Yeah, this image is still real, but the moment you bring it closer than the principal focus, what happens? You have the image being formed on the same side as the object. It is magnified and it is virtual, meaning it cannot be captured on a screen. So if you want to view this image, then you bring your eyes here. Your eyes can be here. And when you bring your eyes here, then you'll be able to see the image with your eyes, but it cannot be captured on the screen because the rays that are coming from the lens are divergent, they are not convergent. So you can only view it with your eyes. That's why you call it a virtual image because it cannot be captured on a screen. So the first thing we have is that we mark the point X, which is the principal, well, we mark the point X on the principal axis for a possible position of the object. So the object must be placed between the principal focus and the lens. So the object can be placed anywhere within this place, okay? And if you want to place it here, fine. Anywhere between the lens and the principal focus, that's where you place the object. Then the second question says a point E for a possible position of the student's eye. The student that wants to view it will come and view from this other side. So your eye will be on this side. Okay, your eye, you can't view it from the same side as where where the image will be formed. Okay, you come and view it from the same, you come and view it from the other side. So the eye will be here. And if you have put X here, then you come and put E on the left hand side so that you have to view it from the other side. Then the next question, underline two words in the list that describe the image produced. If you are using a converging lens as a magnifying glass, the image produced will be virtual. Okay, it can't be captured on a screen, and it's also be upright. Okay, don't forget that when we formed a real image is inverted, upside down. When you are forming a virtual image, the virtual image will be upright. Okay, just the way the object is, image will be upright. So that is clearly understood and clearly noted and done correctly. We move to the next question that says the refractive index of glass used to make the lens is 1.5. The speed of light in air is 3 times 10 to the power 8 meters per second. Calculate the speed of light in glass. The formula for refractive index is speed of light in air or speed of light in vacuum divided by speed of light in the medium. In this case, the medium is glass. We are told that the refractive index is 1.5. The speed of light in air is 3 times 10 to the power 8. The speed of light in glass, that is what we do not know. To find the speed of light in glass, we make the speed of light in glass the subject of the formula. That means speed of light in glass will be 3 times 10 to the power 8 divided by 1.5, and that will give us 2 times 10 to the power 8 meters per second. Without delay, we move to the next question. State what happens to the wavelength of light as it passes into the lens. Okay, take note that the speed of light is changing. And do not forget that velocity of light is frequency multiplied by wavelength. Frequency does not change during refraction. Frequency does not even change. Frequency is number of waves produced by second. It is the frequency that is coming from the source that gets to you and continues that way. The frequency does not change. The only thing that can change are speed and wavelength. So if the speed is reducing, what do you think will happen to wavelength? Since frequency is a constant, then speed is directly proportional to wavelength. Okay, or you say wavelength is directly proportional to speed. So if speed is reducing, then wavelength automatically reduces. That's all. So you tell us that the wavelength reduces, or you tell us that the wavelength gets shorter. Without delay, we move to the next question. We don't have much time. The wavelength, oh, the wavelength gets shorter. That's all. Without delay, let's move to the next question. Converging lenses are used in spectacles, that is glasses, to correct one problem with vision. State the name of the problem and explain how a converging lens is used to correct it. What's the name of the problem? Kindly note that converging lens would help you to focus the rays, okay? So if the rays were going this way, whenever they meet a converging lens, what happens? The converging lens will help us to focus those rays. If the rays were going this way, if they meet a converging lens here, they'll be focused and converge, come together. Now, look at this. If an object is far away, what happens? The, the rays will be converged at a nearby point. But the closer you bring the object, the rays will be converged at a far distance. Now, if I take this point F as the position of the retina of a person's eyes, that simply means if the object is extremely far away at infinity, if the object is extremely far away, then the image can be formed on the retina. If the object is very far away, the image can be formed successfully on the retina. But the moment I bring the object close by, the image will be formed beyond the retina. Long-sightedness means you can see objects that are at long distances. Hence, the image of object that is at a very long distance can be formed on the retina. But the moment you bring the object nearby, the image will be formed behind the retina. Hence, you need a convergent lens to help you to correct this defect and bring the image on the retina. Okay? Long-sightedness means you can see objects at long distances. But whenever the object is nearby, the image becomes far away. The image goes behind the retina. So you need a converging lens to bring that image to the retina, okay? But when the object is at far or long distance, you can see the object successfully. So that defect is called long-sightedness, okay? That defect rather is called long-sightedness, okay? That's the name of the problem. And how do you correct it? This is how you correct it. In long-sightedness, the image is formed behind the retina. Okay, so whenever an object is at short distance, okay, in long-sightedness, the image of nearby objects, I have to state that the image of nearby objects is formed behind the retina. So how do you solve that? So the converging lens is used to reduce the combined focal length of both lenses and focus the image on the retina. The combined focal length of both lenses. What are the lenses we are talking about? That is the converging lens that you are using to correct the defect, okay, and the lens in the eye, okay, yeah, the lens in the eye. So the converging lens would help us reduce the combined focal length of both lenses, okay, and as a result, the image will successfully be formed on the retina. Without delay, let's move to the next question. Question number 5. Let me come to this place so that you can solve the brand new question. Describe how a longitudinal wave differs from a transverse wave. In the case of longitudinal wave, the direction of vibration of the particles is parallel to the direction of motion of the wave. Okay, yeah. So the direction of vibration is the same thing as the direction of travel of the wave. That is a longitudinal wave. But for a transverse wave, the direction of vibration is perpendicular to the direction in which the wave travels. That's it, and that's the distinction between a longitudinal wave and a transverse wave. Easy. So we take the next question. Figure 5.1 represents a seismic wave produced by an earthquake. Don't forget that earthquake produces two types of seismic waves. We have the P wave, the primary wave, and the S wave, the secondary wave. And the best way to get that distinction, just imagine P, series of P's being written, and that describes or that illustrates the shape of longitudinal wave. Okay, and as for the S wave, imagine series of S being written, S, 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 and that exactly is the shape of transverse wave. So the truth is that the P waves are longitudinal wave and the S wave are transverse wave. Yeah, so those are the two types of seismic waves that are produced during earthquake. The P wave, which are primary wave, and S wave, which are secondary wave. The question says, state whether this seismic wave is a P wave, primary wave, or S wave, secondary wave. Justify your response. It is a primary wave. I did not justify. I must have forgotten. Why do we call it a primary wave? You can see from the shape of the wave, it has regions of compression and regions of rarefaction. That's all. Okay? It has compressions and rarefactions. That's it. And you get your full mark for that question. Without delay, let's go on. The second part of the question says, let me pick that from here. The wave represented in figure 5.1 has a wavelength of 1.2 times 10 to the power 4 meters. Calculate the actual distance between the point J and point K. Okay, let's look at the wave again and talk about the point J and point K. So this is J, okay, where we have a compression, and this is K, where we have a rarefaction. Don't forget that the distance between this compression here and the next compression is a wavelength. And the distance between this compression here and this rarefaction is half of a wavelength. Okay, therefore we can conclude that the distance between J and K is 1.5 wavelengths, or you call it 3 wavelengths over 2, yeah, or you call it 3 over 2 wavelengths. So that's how you get the distance. The distance JK is 3 over 2 of a wavelength. Good. So calculate the actual distance between J and K. How do we get the distance between J and K? If the wavelength is 1.2 times 10 to the power 4, then the distance between J and K will be 1.5 of this value of wavelength. That's all. So the distance between J and K is 1.5 of lambda, okay, or you call it 3/2 of lambda, okay. That will be 3/2 multiplied by the wavelength is 1.2 times 10 raised to the power 4. 1.2 divided by 2 gives me 0.6. 0.6 times 3 is 1.8. So I have 1.8 times 10 raised to the power 4 meters. Yeah, that's what I have here. So the second part of the question says, the wave in II travels through the ground at a speed of 4,600 meters per second. As the wave passes a certain point, the ground completes 5 oscillations. Calculate the time it takes for the wave to pass. Show your working. Okay, now if we have the speed of the wave and we have the wavelength, then we can get the frequency. You know, V equals to F lambda, right? Yeah, that means frequency equals to V divided by lambda. But do we need frequency? No. What we need is the time taken to make one complete oscillation. Yeah, we are looking for the time taken to make 5 oscillations. So first of all, let us get the time to make one complete oscillation. If we get the time to make one complete oscillation, we multiply it by 5 to get the time taken to make 5 complete oscillations. What is the time taken to make one complete oscillation? In physics, that is defined as period. Period. And period has the symbol T. And T is 1 over frequency. So if I divide 1 by the frequency, I will get the time taken to make one oscillation. Since frequency is V over lambda, automatically 1 over frequency gives us lambda over V. And that is period, because period is 1 over F. So the formula I'm using here is period equals to wavelength divided by velocity. The wavelength is 1.2 times 10 to the power 4. 1.2 times 10 to the power 4. That is 12,000 to me though. Yeah, that's 12,000. Divided by velocity is 4,600. Now, if you use your calculator to divide 1.2 times 10 to the power 4 by 4,600, let me see what I got when I did that. I got 2.6 seconds. Yeah, so I have 2.6 seconds. That's the period. So the time for 5 oscillation is 5 times the time for 1 oscillation, which is period. So I have 5 times 2.6, which will give me 13 seconds. The time here is 13 seconds. Yeah, so that's the time taken. And that's that about that. Let's move to the next question. Let me pick it from here. Figure 6.1 shows an isolated metal sphere suspended by an insulating thread from the ceiling. The sphere is negatively charged. The charge on the sphere produces an electric field in its surrounding. State what is meant by electric field. The region of space where a charge experiences a force. That's it. An electric field is the region of space where a charge experiences a force. Let's see. Region of space where a charge experiences a force. That's it. Okay, let's see the next question. Let me just use this one. So draw on figure 6.1 to show the pattern and direction of electric field produced by the charge on the sphere. Draw at least 4 lines. Electric lines of force. You were told that the the object, the sphere, is negatively charged. Yes, you were told that the sphere is negatively charged. So if the charge on the sphere is negative, the lines of force around a negatively charged object radiate inwards. Like, you have the lines of force, but your arrows must point inward. So that's how you indicate the electric lines of force. Yes, that's it. Once you do that, you get your full mark for that question. The next question. The magnitude of the charge on the sphere is 3.5 times 10 is the power minus 10. That's Q. An earthed metal wire is touched against the sphere, against the surface of the sphere, and the sphere is discharged. State what happens in the wire as the sphere is discharged. And since sphere is negatively charged, okay, the moment you use an earthed object to touch this sphere, let's assume this is the earthed object. Let me put the symbol of earthing. So if this is the earthed object, what simply happens is that all these electrons will flow through this metal wire. That's all. Yeah, all these negatively charged electrons, they will all flow through the metal wire and into the ground. That's all. That's it. So that's what I've written here. Electrons will flow through the wire into the ground. That's all. Okay, the next part of the question is that it takes 0.14 nanoseconds for the sphere to discharge completely. Calculate the average current in the earthed wire as the sphere is discharged. The formula for current is the quantity of charge divided by time taken for that charge to flow. Yeah, I equals to Q over T. What's the quantity of charge? 3.5 times 10 to the power minus 10. So I have 3.5 times 10 to the power minus 10 divided by, the time is 1.4 nanoseconds. 1.4 nano means 10 to the power minus 9. Yeah, nano means 10 to the power minus 9. Don't forget, milli means 10 to the power minus 3, micro means 10 to the power minus 6, nano means 10 to the power minus 9, pico means 10 to the power minus 12, femto 10 to the power minus 15. But they wouldn't get up to all of that. I'm sure IGCSE syllabus does not go beyond nano. So let's see 3.5 times 10 to the power minus 10 divided by 1.4 times 10 to the power minus 9. If you use your calculator for that, minus 10 minus 9 minus 1. Okay, that will be 0.35 divided by 1.4. That's a shortcut. That will give you 2.5. Hold on, please. Minus 1. Let me finish this. Okay, and when I did this calculation, I got um 0.25 because I mistakenly wrote this 0.14 as 1.4. This is 0.14, so I should write 0.14 here. 0.14. So if I use calculator for this, then I'll get 2.5 amps. Okay, yeah. So let's proceed to the next question. 2.5 amps. Let me confirm that from the people I've done before. 2.5 amps. Okay, that's it. We move to the next question. An electromotive force EMF of a battery is 7.5 volts. Define the term electromotive force. An electromotive force, that is work done per unit charge. Okay, it's work done or energy converted, electrical energy converted in moving um, charges around a circuit. Okay, so see the way I stated it here, the electrical work done in moving a unit charge around a complete electrical circuit. And the charge particles are the electrons. So in moving a unit charge around a complete electrical circuit. The second question says, the battery is connected in series with a variable resistor and a 30 ohm resistor. The battery is made using 1.5 volt cells. Draw a circuit diagram that shows all 1.5 volt cells connected to produce an EMF of 7.5 volts. First of all, starting with the 1.5 volt cells, we have 1.5 volt cells. Okay, so if you do 7.5 divided by 1.5, you get 5. So we need to connect 5 cells in series, okay, in order to get the total of 7.5 volts, okay. 1, 2, 3, 4, 5. Yes. So we have connected 5 1.5 volt cells in series in order to get our in order to get our 7.5 volts. Yeah, so that is it. We need a variable resistor. Okay, you connected it in series with a variable resistor and a 30 ohm resistor. So you have to connect it in series with a variable resistor and a 30 ohms resistor. So these are fixed resistor, our 30 ohm resistor. Yes, that's it. So you have to draw the circuit, which we have just done. The next question says, the resistance of the variable resistor can be varied from 0 ohms to maximum resistance of 150 ohms. Using the axis in figure 7.1, draw a graph to show how the current in the circuit varies with the resistance of the variable resistor as it increases from 0 ohm to 150 ohms. Determine and label the value of the maximum current on the y-axis. Maximum current. When would this circuit produce the maximum current? This circuit produces the maximum current when the resistance of the variable resistor is 0. Okay, don't forget that the voltage of the battery is 7.5 volts. So when the resistance of the variable resistance is 0, what will be the current? I equals to V over R. So I equals to V over R. What's the voltage? The voltage is 7.5. Resistance here is 3 ohms, 30 rather. 7.5 divided by 30 will give me 0.25 amps. That's the maximum current that this circuit can deliver. Why did I say that? Because the maximum current can be gotten when the resistance of the variable resistor equals to 0. So whenever the resistance of this variable resistor is 0, the current flowing in this circuit is maximum. Okay. Yeah. So when they said determine and label the value of the maximum current, the value of the maximum current which we have here will be 0.25 amps. I don't need to put amps here because current is already labeled in amps here. So what you just do is that once you do that, and then you just draw a line here, which is the slope, and that is what we have here. So let us use a first simulation to explain this concept we've talked about. So here I have connected five cells in series. The voltage of each of them is 1.5 volts. The voltage of each of these cells is 1.5 volts. I've connected them all together in series, and the total voltage of all these five cells is 7. The total voltage of all these five cells, let me see, 1, 2, 3, 4, 5, 6. Oh, I mistakenly put 6. So let me remove one from these cells. I was supposed to just click on one and delete it. So I have five cells now, and the total voltage of all these five cells is 7.5 volts. So let me connect my voltmeter again. Yeah, so now I'm doing it correctly. 7.5 volts. My fixed resistance 30 ohms. My variable resistor, I've reduced the resistance to 0 um, ohms. What's current here? 0.25 amps. So the maximum current you can have is 0.25 amps, which is the current when the resistance of the variable resistor is 0. Now I want to come and increase the resistance of my variable resistor. As the resistance of the variable resistor is increasing, keep an eye on what is happening to current. As I'm increasing the resistance of the variable resistor, what happens to current? Current is decreasing. Okay, current continues to decrease. At 120 ohms, current is 0.05 amps. So that is what I've illustrated here. Okay, as resistance as the resistance of the variable resistor increases, current decreases. So this is the kind of graph you should have. Okay, so if you want to be more detailed, you may choose to label, put all the other smaller divisions like 0.0, 0.05, 0.10, 0.05, 0.10, 0.15, 0.20. Okay, yeah, you may choose to put other smaller divisions and even put the value of the current when the resistance here is 150. You know, when the resistance of a variable resistor is 150, what will be the current? I equals to V over R. Okay, the voltage is 7.5, resistance is 180 ohms. That's the total resistance. Why? When the resistance of the variable resistor is 150 ohms, the total resistance in the circuit is 180. Why did I say that? Because the variable resistor is in series with the fixed resistance. Okay. Yeah. So when the resistance of variable resistor is 150, total resistance in the circuit will be 150 plus 30, which is 180. Oh, sorry about that. Okay, yeah. So if I divide 7.5 by 180, I should be getting 0.042 or something like that. Yeah, so at 150, the current should be around that value. Don't I have 0.04? So just make sure you are very creative when drawing this slope. Make sure you start from 0. and try to match where it ends with the value of current when the resistance is that value. So we move to the next question. The next question is on radioactivity, and let's see. Question 8. The isotope thallium-208 is radioactive. It decays by beta decay. Thallium-208 decays to an isotope of lead. Complete the equation for this decay. Okay, we have a beta particle here. Beta particle have a charge of -1 and mass of 0. So let's fix this. 81, we have -1 here. There's a number we put here that if you minus 1 from it, we get 81. What number is that? That will be 82. Yeah, because 82 minus 1 gives us 81. There's a number here that if you add 0 to it, we get 208. What number is that? That will be 208. That's it. So that's what happens when lead, that's what happens when thallium becomes lead by emitting beta particles. So the beta emission of thallium-208 is accompanied by gamma emission from the nucleus. Explain why the gamma emission does not affect the nucleus, does not affect the numbers rather in equation AI. Why doesn't it affect the number? Because gamma ray have a mass of 0, and the charge of 0. So there's no change in these numbers, okay? Gamma rays have a mass of 0 and a charge of 0. And that is what we have here. Okay, gamma rays have a mass of 0 and a charge of 0. Gamma rays have 0 mass and 0 charge. That's it. The next question says, state one reason why the nucleus of thallium-208 is unstable. Look at thallium-208. What is the number of protons? It has 81 protons. And how many neutrons does it have? Let's do 208 minus 81. What would that give you? 8 minus 1 is 7. 20 minus 8 is 12. So it has 127. Let's see. Yeah, it has 127 neutrons. So the number of protons and neutrons, are they equal? No. The number of neutrons far exceed the number of protons. So it has excess neutron, okay? Yeah, it is massive and it has excess neutron. So because of that excess neutrons that it has, then the nuclear forces are not balanced. Yeah, the nuclear forces need to be balanced for it to have a stable nucleus, or at least the atom must be small. But when an atom is massive, nuclear force is not balanced, then you definitely have a radioactive atom. So what do you have here? It has 82 protons and 126 neutrons, okay? Hence, it has 81 protons. Yeah, we are talking about thallium, not lead. It has 81 protons. It has 81 protons and 126. Is it 126? Is 127 neutrons. We are talking about thallium, not lead. It has 81 protons and 127 neutrons. Hence, there are unbalanced nuclear forces in its nucleus since it has excess neutrons. Yeah, so it has more neutrons than protons. Okay, then the next part of the question says, a sample of thallium-208 is placed in a thick lead container. Figure, hmm, hold on, please. I was supposed to talk briefly. After explaining this, I was supposed to talk about the simulation. Hold on a minute. So if you look at this, oh, okay, it's fine. As long as you understand the concept. So let me just use this simulation to explain this quickly. This is our thallium-208, okay? Atomic number 81, atomic mass 208. And you can see this beta decay, beta minus is highlighted here. Half-life is 1.8 times 10 to the power 2 seconds. That's 180 seconds. So if I click on this beta decay, you see it will fire off an electron This color blue is electron. It fires off an electron, okay, and one of the neutrons will be converted to a proton. It fires off an electron. I'll click on this. Keep an eye on what is being fired off from the nucleus. I'll click on this now. You see, it fires off an electron, okay, and take note of the changes. It's no longer thallium 81, it's now lead, atomic number 82, atomic mass remains 208. And that is what we have on the equation. So the simulation explains what the equation is telling us. And the next question says, a sample of thallium 208 is placed in a thick lead container. Figure 81 shows a narrow beam of beta particles and gamma radiation. Beta and gamma are here, emerging from a small hole in one side of the container. We have the magnetic field. This X means magnetic lines of force are pointing away from us and into the paper, okay? So magnetic lines of force pointing away from us and into the paper, all right? Good. Don't forget we are using Fleming's left-hand rule. So what else do we have? The magnetic field is pointing to what direction? Magnetic field points this way. So what's the direction of the resultant force now? What's the direction of deflection of the what's the direction of deflection of the beta particles? That are indicated here. The direction of deflection of beta particles is downward. Why? Because if we consider this Fleming's left-hand rule, if you consider Fleming's left-hand rule and you try to arrange the fingers of our left hand such that if we try to arrange the no, let me do this again. If I use Fleming's left hand rule, arrange the fingers of my left hand such that the index finger points in direction of field and the middle finger points in direction of current, what will I have? Then direction of my thumb gives me the direction of deflection. Okay? Yeah. Direction of my thumb gives me direction of deflection. So I'll do this again. The middle finger points into the page, okay, away from me, into the page. And the index finger points in direction of field. What's the direction of my thumb? Direction of my thumb gives me direction of deflection. And what's the direction of my thumb here? Upward. Take note that the direction of thumb here is direction of deflection for alpha particles. And direction of deflection using Fleming's left-hand rule is direction for alpha particle. So for beta particle, it will be opposite of that. Okay? What I got was upward, only for alpha particle, but for beta particle, it will be opposite of that. So beta particle will be deflected downwards. Okay? Yeah. And I'll label it beta. That's the direction of deflection of beta particle, downward. Then what else there was a question asked for? The one for gamma rays will go undeflected. Okay, I'll label that gamma. That's it. That's what the question asked me. Okay, draw a line for beta particle, another line for gamma rays. That I have done correctly. With that, then we go to question number 9. The sun is one of many billion stars in the Milky Way. The sun emits very large quantity of energy as electromagnetic radiation. State the three regions of electromagnetic spectrum in which the sun emits the most energy. That's the visible light, the one before visible light, the one after visible light. The one before visible light is infrared, okay? The one after visible light is ultraviolet. So we have infrared, visible light, and ultraviolet rays. That's all. Second question, electromagnetic radiation from the sun travels at the speed of 3 times 10 to the power 8 meters per second. The radiation takes 500 seconds to reach the Earth. Calculate the distance from the sun to the Earth. Speed is distance over time. That means distance is velocity times time. The speed of light is 3 times 10 to the power 8. The time is 500 seconds. So if I multiply 3 times 10 to the power 8 by 500, what will I get? 5 times 3 is 15. So I have 15 times 10 to the power 10, which is 1.5 times 10 to the power 11 meters. 1.5 times 10 to the power 11 meters. Yes, that's it. Or you call it 1.5 times 10 to the power 11 meters. Okay, or 1500 megameter, your choice. 1500 megameter. The next question says, approximately 4.6 billion years ago, the sun formed from an interstellar cloud of gas and became a stable star. Describe and explain what happens as the interstellar cloud of gas forms a protostar. Okay, it became a stable star. Okay, so from interstellar cloud of dust and gas to stable star. But first of all, we want to talk about how it forms a protostar before talking about how the protostar becomes a stable star. So actually, in the life cycle of a star, it starts from a stellar nebula, which is the interstellar cloud of dust and gas. This is the interstellar cloud of dust and gas. So the interstellar cloud of dust and gas, then the inward force of gravity begins to pull all these gas particles and dust particles together. As it continues to pull them together, after some time, this gas particle then begins to wheel. That means they begin to move in a circular path. It begins to move in orbit, form an orbit, okay? Yes. So this cloud of dust and gas, gravity pulls them inward. As gravity is pulling them inward, after some time, because of the unbalanced inward forces, they begin to turn around and move in circular paths. And at that stage, as the particles are moving and colliding with each other, friction causes heating. The temperature of that gas becomes higher. The temperature begins to increase, and that inward force due to gravity continues to increase the pressure inside. Okay, yeah. So let's assume this is an interstellar cloud of dust and gas, and the particles are moving around in circular orbits. The fact that gravity continues to pull everything inward, the middle becomes hotter. Okay, and due to the high pressure in the middle, as a result of everything coming in together. So in the middle of it becomes hot, okay, and pressure will be high. Because of that high temperature and pressure, nuclear fusion can start, okay? Yeah, nuclear fusion begins. And that stage, we say we have a proton star. Nuclear fusion begins. And what is happening? Hydrogen begins to combine to form helium. Hydrogen begins to combine to form helium. That is what happens here. So that is that about that. That is what happens here, though in the process a neutron might be produced. Yes. So that is what happened here. And what's next? After some time, the nuclear fusion that is happening in the core, in the center, it then causes the pressure in the middle to build. I know when pressure in the middle is building, then there will be an outward force trying to pull everything apart. And don't forget that gravity still remains in action, and gravity continues to try its best to pull everything inwards. Okay, while the outward force due to high temperature is trying to push everything outwards. The outward force due to high temperature and pressure, that are represented with the red arrow. The inward force due to gravity are represented with the green arrow, trying to pull everything inward. So when the inward force due to gravity is equal to the outward force due to the high temperature and pressure in the core, whenever those two forces are equal, then we say we have a main sequence star, okay, or a stable star. You understand that? Good. So when we have a main sequence star, then this stage can last for millions of years, okay, hundreds of millions of years. So after a very long period of time, if it is a massive star, okay, then it becomes a red giant. No, like massive star, not actually massive though, but if it is a star of the size of our own star, the name of our star is the sun. You know, the sun is a star. Yeah. So let's just say um moderate size, or yeah, moderate sized star, moderate size, sorry, the word is medium, medium or small stars. A star can be as small as our Earth, as the Earth in our solar system. Medium and small size star can become red giants, while massive stars or a super massive star will become a red supergiant. How does this happen? This is what happens here. You know, at that stage called main sequence star, when the temperature, when the nuclear fusion, when all the hydrogen fuel has been exhausted, not all completely though, but when majority, when the star is running out of hydrogen fuel, what happens? The process of nuclear fusion will slow down, and that will cause the drop in temperature of the star. As a result of that drop in temperature, because nuclear fusion has become has almost stopped, nuclear fusion has reduced drastically, the outward force becomes reduced. Hence, gravity would cause everything to collapse and become smaller. As gravity makes it smaller, you are shrinking a very hot, massive star. So when it shrinks, then it becomes extremely hot again. It becomes so hot and white hot that at that temperature and pressure, nuclear fusion will be forced to start again. And at this stage, it is no longer hydrogen that acts as the fuel. It is helium that acts as the fuel. Helium begins to fuse together to form carbon, to form boron, and boron begins to fuse together to form carbon and heavier. All the heavier atoms will be formed at this second stage. And that now causes the star to become massive and far bigger than it was. If it was of this size, at this second stage, it can become as big as something like this. Yeah, it can become as big as something like this. So that is what happens during this second stage. And at that stage, let me say we have a red giant. Okay, that's if the star was a medium size or small star. But if it was a massive star, then it forms a red supergiant. And the red giant in its case, after some time, it explodes as planetary nebula, giving off some gas into space. Okay, it explodes as planetary nebula. The core then becomes a white dwarf, which is just a very small, hot, massive star. And after some time, the temperature of the white dwarf reduces and it becomes cold and it becomes a black dwarf. And at that stage of black dwarf, it is just an extremely dense and massive spherical rock moving in space. So that is it, and that is how it ends its life cycle. But in the case of a, a supermassive star, when it becomes a red supergiant, the red supergiant explodes as a supernova. The supernova is considered the brightest thing ever known to mankind. A supernova can outshine an entire galaxy. You know, a galaxy can contain 100 billion stars. One supernova alone in this galaxy can outshine all the stars in the galaxy combined. So the red supergiant explodes as a supernova, giving off gases and all the elements that have been formed, okay, giving off all the elements that have been formed, pushing it out into space. Okay, so if it is a massive star, then after exploding as a supernova, it forms a neutron star. But if it is a supermassive star, after exploding as a supernova and giving off gases into the space, the core forms black hole. It is the core that forms either a neutron star or a black hole. Yeah, and that's what I've been explaining here. Okay, so when this one explodes, the center here is what becomes either a neutron star or a black hole. It becomes a neutron star if it is a massive star, and if it is a supermassive star, it becomes a black hole. How are they different from each other? In the case of a neutron star, the density is so high that atoms begin to collapse. Yes, you know, an atom that has protons, neutrons in the middle, and electrons on the shell, this atom will collapse completely. Collapse. The proton, neutron, and electron will come together as one. And when they come together as one, proton and electron will combine to form a neutron. Okay? Why the neutrons remain the way they are. So if proton and electrons are combining to form a neutron, so neutron, everything will be neutron, okay? So there will be no proton, neutron, electrons, no. Everything in the atom become neutrons, okay? Yeah, because proton and electron will collapse together to form a neutron, okay? So the neutron here plus the neutron that has been formed, everything will be neutron. That's why it's called a neutron star, because everything in this star is a neutron, and the density is extremely high, gravity extremely high, but it can still give off light because the gravity is not high enough to pull in light. But for a black hole, the gravity is so high that even rays of light cannot escape from a black hole. This is a detailed explanation of the life cycle of a star. So let us bring this knowledge into answering this question. Describe and explain what happens as the interstellar cloud of gas forms a protostar. Well, the inward pull of gravity causes the nebula to shrink and starts wheeling. Okay, it begins to move around. Okay, this causes an increase in temperature. This high temperature and pressure causes nuclear fusion to begin. And during nuclear fusion, hydrogen atoms begin to fuse together to form helium atoms. That's all. Um, yeah, hydrogen fuses together to form helium. Then in the second one, describe and explain what happens as a protostar becomes a stable star. For that to happen, the outward force due to high temperature and pressure as a result of nuclear fusion in the protostar must become equal to the inward force due to gravity. So a stable star is then formed at that stage, okay? And this stage can last for hundreds of millions of years. This brings us to the end of this past question paper. My intention was to solve all of this within 45 minutes, but the additional explanation made it 1 hour 15 minutes, so 1 hour 12 minutes. Thank you for joining us today. Please subscribe to this channel. And if you need personalized tutoring, okay, personal tutorial to guide you to ensure you make excellent grades in your examination, reach out to me, send an email to me, okay? Yeah, send an email to me. You know my email address? You don't know my email address? physics.4.everybody@gmail.com. Send an email to me. Thank you for joining us today. See you on the next video. Have a nice day. Goodbye.